We will continue our discussion on IC engine, and today we will discuss about CI engine injection system. We have started our discussion on CI engine injection system, but we will continue with that, and then we will briefly discuss about the air cooled and liquid cooled engines. So, we have discussed about the we have seen that compression ignition engine injection system can be classified into two categories. One is air injection system, another is solid injection system. We have discussed about the air injection system, and we have seen that nowadays it is obsolete now because of the cost associated with the big size compressor as well as its running cost. And then we have discussed about the solid injection system, which is further subclassified into three categories: common rail system, individual pump and nozzle, and then unit injector. So, we have discussed about the common rail system, and if we try to see what are the disadvantages are associated. I mean, what are the disadvantages associated with this injection system. So, if we try to recall, I won't draw the schematic again because last class I have drawn the schematic. Just I will try to draw the this is the engine cylinder only to work out a few analytical expression. Then if this is the engine cylinder, so this is cylinder and this is nozzle. We will discuss about one by one, and if we try to recall that pressure at the cylinder was P1. So, here pressure is P1 and here pressure is P2. So, P2 the pressure at nozzle and P1 is the pressure in the cylinder. Now, if I try to that we need to know what is the mass flow rate of fuel, because let me tell you in this common rail system we have seen that there is a common rail in which the pressure is remaining constant. So, that is if pressure changes, there is a system where we can maintain a constant pressure by regulating certain amount of fuel through throttle valve. That is because the common rail system is connected to the high pressure pump. So, the high pressure pump build up that pressure and essentially to maintain a pressure constant in the common rail system. In case pressure rises above the design pressure of the common rail system, then liquid fuel is taken back to the inlet to the common rail system through a throttle valve. This is regulated. So, pressure head is constant by a pressure regulating valve or throttle valve. So, we can see that the pressure, we have seen pressure in the common rail is constant, rather this constant pressure is maintained, by a pressure regulating valve, by a pressure regulating valve or by throttling. That is what we have seen. Now, the maximum pressure under direct control and metering problem is not handled by the high pressure pump. So, high pressure pump is used to build up the pressure which is required to maintain a constant pressure at the constant pressure in the common rail, but the maximum pressure under direct control, unlike displacement pump we have seen, and not only metering problem is not handled by the high pressure pump. Hence, extreme accuracy in manufacturing is not demanded, but we have seen that metering control, that is one of the objectives of having a CI engine injection system. Metering control is not handled by the high pressure pump, that is HP pump. And very important, so how we can control metering So, this is not the function, there is no functional element to control the fuel into the cylinder. That means, this high pressure pump is used only to maintain a constant pressure which is required at at the commonwealth system. Now, this metering, this control, the high pressure pump is not used to control the liquid which is being injected or which is being supplied into the cylinder. That means, discharge from the nozzle, discharge from the nozzle is regulated by the size of the metering orifice, by the size of the metering orifice and pressure drop in the delivery lines. Hence, since this is very important, hence the nozzle must closely match to ensure, hence nozzle must be closely matched to ensure equal distribution among cylinder. This is very important. That means, since we do not have metering control and the discharge from the nozzle depends upon the size of the nozzle metering orifice that is there in the nozzle and the pressure drop in the delivery lines. Therefore, nozzle must be designed in such a way that it will match closely to ensure equal distribution among the cylinder. Since now we will see, because of this, the since nozzle itself is an important element for this injection system, since we do not have any metering element, we will see because of this the nozzle orifice clogging or the wear of the nozzle orifice creates a problem and it becomes a serious disadvantage for this particular injection system. We will discuss. Now, since the discharge from the nozzle is regulated by the size of the metering orifice and as well as the pressure drop in the delivery line. So, that is why now we need to know that what is the mass flow rate being, what is the discharge from the nozzle, and for that we will do this simple analysis. So, that is why you have seen that at the time of injection, so this is at the time. So, this is the pressure at the time, these are the pressures at the time of injection. Now, we will now see again that if this is the nozzle and this is the cylinder, so this is section pressure is P2 and this section pressure is P1. So, P1 and P2, so this is nozzle and this is cylinder. So, now we need to know pressure drop. So, if P2 and P1 are the pressures at the time of injection, right. So, now maybe we can write if T is the injection time and theta is the injection period and N is the RPM of the engine and N is the RPM of the engine. That means, if we try to recall that, maybe injection starts over here, injection ends. So, this is end of injection, this is start of injection, and this angle theta is the injection period. So, this is theta, this is injection period, that is what we have seen. Now, we can relate this total time injection period in terms of t and n. So, how can I? Now, we have seen that this 360 degree, the crank will move 360 degree in one revolution, and if the speed is n, that is n revolution in 1 minute or 60 second. Therefore, one revolution will be 60 by n second. Therefore, I can write 360 degree is equal to 1 revolution is equal to 60 by n second. Therefore, if the injection period is theta degree, then time t, then 60 by n into theta second. So, by 360. Therefore, that is equal to theta by theta n into 6, theta n by 6 n second. So, the injection time t, so injection time, if injection period is theta, then injection time t will be equal to theta by 6 n second. That is what we have seen or we have calculated. Now, we will apply the assuming that there is we can write the Bernoulli equation between point 1 and 2. So, if I write Bernoulli equation between point 1 and 2, then I can write this P2 by rho g almost equal to P1 by rho g plus C1 square by 2, C1 square. So, pressure exactly at the here P plus C1 square by 2. So, 2g. Therefore, I can write that C1 will be equal to root of twice into P2 minus P1 divided by rho, this is rho of fluid, rho of fuel, rho f. Mass flow rate will be equal to rho f into area into C1, that is equal to A1, I am writing area is A1 at the, this is the pressure very close to the nozzle outlet. So, P1 is the pressure at nozzle outlet and area is equal to A1. So, this is A1 into root of twice rho f into P2 minus P1. So, this is the mass flow rate that rho A1 into 2 rho f into P2 minus P1. Now, what will be the kg of fuel supply per cycle. So, we have seen the injection time per cycle, injection time is theta by 6n. So, what is a kg of fuel supplied per cycle? So, we have calculated mass flow rate. So, this is mass flow rate of fuel. So, this is mass flow rate of fuel. We have calculated pressure drop, from there we have calculated velocity C1 at the nozzle outlet, and from there we have calculated mass flow rate. Now, we can easily calculate kg of fuel supplied per cycle, that will be equal to m dot f into total, that will be equal to m dot f into injection time. So, this is injection time. So, that will be equal to A1 root twice rho f into P2 minus P1 into theta by 6n. So, this is mass flow rate per cycle. So, now I can tell important that the expression, this is a very important expression. So, we have discussed about the common rail system, right. So, what is evident from this expression, that kg of fuel supplied per cycle is very important, that quantity, that is the fuel quantity delivered so so what I can see from this expression, it is evident from the expression of kg of fuel supplied per cycle that the fuel quantity delivered will decrease with increasing speed. So, from this expression it is evident that fuel discharged or the amount of fuel discharged will decrease with speed n unless theta is increased to maintain theta by n this quantity constant. Therefore, we can't ensure that at varying loads, at varying speed, the amount of fuel to be supplied into the cylinder will remain constant, and that is why the requirement, this requirement introduces mechanical complication the common rail system, and this common rail system is not often used except an engine designed to run at constant speed. So, what I can see from this expression, this is a serious disadvantages. So, what is the disadvantages? Now, I will write. From this discussion, we can see the amount of fuel discharge will decrease speed unless theta is increased to maintain theta by n constant. That means, we can't say that this system will be appropriate for an engine where we can have where the engine may engine may need to run at varying loads or varying speed. That means, this is an important system. So, this requirement that is what we have discussed above, and this requirement introduces or leads to mechanical complication in the common rail system, right, and that is why this system is not often used. The system is not often used except an engine designed to run at constant speed. So, if we design an engine to run constant speed, then it is fine. Otherwise, if a particular engine needs to run at different loads and different speed, then this system is not appropriate. So, this may be one. Another important disadvantage is that is what we have discussed, that there is no metering control. So, the nozzle orifice, the metering orifice is important for the supply of the size of the metering orifice is important to supply the required quantity of fuel that will be discharged into the cylinder. Therefore, this is a serious disadvantage of common rail system is that this very important that CDF that we will multiply, because if we go back I forgot to maintain that this quantity is not equal. So, that is why I have written the mass flow rate will be equal, nearly equal to the, almost equal to the this, but the actual mass flow rate m dot f actual will be always less than that, because to frictional pressure drop we did not consider. So, that will be equal to CDF A1 2 rho f into P2 minus P1. Now, this CDF is very important, that CDF discharge coefficient of the fuel is very important. CDF is sensitive to wear of the nozzle, wear of the nozzle and of the needle point. If we try to of the needle point, very important, and to deposit of solid matter, very important, because fuel is a family of hydrocarbon on the needle and the nozzle orifice, on the nozzle orifice. Since there is no metering element, separate metering element, right. So, metering orifice of the nozzle or nozzle orifice controls the fuel amount to be discharged into the cylinder, that depends upon the initial design values. So, after keep on using or keep on continuously keep on supplying fuel, there might be a problem that there might be a solid deposit at the nozzle orifice, which may not give the proper supply of fuel. So, this is serious burden. So, this is serious problem. So, these two are the disadvantages associated with the common rail system. That is why this system is nowadays almost obsolete, unless we require a constant speed. Even though the engine is designed to run constant speed, but still the problem of solid deposition at the nozzle orifice is there. So, that is why this system is not used nowadays. Next, we will move to discuss about individual pump and injection system. So, now we will discuss about individual pump and injection system. Also very important, but I have to draw the schematic again and then I will discuss. Important is this system is also again this system is also having disadvantage, but I will discuss that how this system is working and again how can we control. So, now I have to draw the schematic. There is a two different side, one side is known as pump side, this is cylinder, then this is schematic. So, I am just drawing schematically different parts of this system. So, this is the there are two different sides, but they are connected. This is pump side and this is injector sides, nozzle side. This is cylinder, this is inlet port through which high pressure fuel inlet port. This is spill port, this is spill port, this is plunger of the pump, this is delivery valve, this is delivery valve, this is delivery valve spring, this is delivery line, and this is cam, and then we have a this is injection side. I forgot to write. This is injection side. This is needle. This is fuel passage, this is the fuel passage gallery, or this is needle. This is fuel pressure gallery, this is leak or return, leak return. Now, this is cylinder we have identified, and we have another important unit that is known as with control rack. So, this is control rack, very important. Now, these are the different parts of the individual pump and injection system. So, very important. Now, I can draw the if I draw the again cylinder plunger. So, pump plunger. So, this is Peel's port, this is a cylinder, this is intake, and we have maybe plunger. So, now if this is spill port, so we will have a groove like this, and those are like this, connected like this. So, now this can be rotated, this plunger can be rotated. Now, I will discuss now. So, fuel under a pressure of 40 psi flows through the final filter and then through the inlet port of the plunger and barrel assembly. So, this is the pump side. So, fuel I am writing now. So, number 1 is fuel under a pressure of 40 psi, fuel under a pressure of 40 psi flows through final filter and through the inlet port, through final filter and through the inlet port. Fine, this is very important. When the plunger compresses the fuel, so okay, let me write, when plunger compresses the fuel, the delivery valve opens and fuel flows through the discharge tubing of the nozzle. The delivery valve opens and fuel flows through the, this is very important, that fuel flows through the discharge tubing to the nozzle, through the discharge tubing or delivery line to the nozzle. Okay. Now, if I go back to my previous slide, so the inlet port and spill port are diametrically opposite. Now, when the fuel under a pressure of 40 psi flows through the inlet port of the, this is a pump barrel or pump cylinder, and then the plunger, if it compresses, the upward movement of the plunger compresses the fuel, the pressure which is built up because of the upward movement of the plunger, that opens the delivery valve. Since it is spring loaded valve, a common tendency of the valve will be to sit. So, I mean, again I am telling that whenever plunger is compressing the fuel that is entered through the inlet port into the cylinder, that compression process itself will raise the pressure inside the cylinder, and that pressure will try to open the delivery valve, since it is spring loaded valve. Since it is spring loaded, so the natural tendency of the valve will be I mean to sit over the valve seat. So, these are the valve seat. So, these are the valve seat. So, these are the valve seat. So, a common tendency or normal tendency of the valve will be to sit, rather to be seated over the valve seat, on the valve seat. So, since it is spring loaded valve, it will always be seated on the valve seat. Now, the pressure rise because of the compression of the plunger, I mean compression process, that is a plunger when compresses the fuel, the valve will open and then fuel will flow through the delivery line into the cylinder. That part I will discuss later. For the time being, let us discuss about the other processes. So, this is the process. Now, the nozzle is from the orifice which is closest spring loaded valve. The pump, so nozzle is, again I am telling, the orifice, this is nozzle. So, nozzle is formed by the orifice. Nozzle is formed by the orifice which is closed by spring loaded valve. So, here you can see, I can see that as I write, the nozzle is formed by the orifice which is closed by a spring loaded valve, That means, again I go back. So, the orifice itself acts as a nozzle. Now, the needle, it is a spring loaded. So, the common tendency of the needle again will be I mean remain closed, rather it will remain closed on the opening area of the orifice, so that the entire orifice will remain closed. So, nozzle is formed by the this I have written nozzle is formed by the orifice which is closed by spring loaded valve. So, needle will be always seated on the gap between that fuel passes between the cylinder and the upper part of this injector side. So, it will always remain seated, fine. Now, another problem is, here we are having cam and follower mechanism. So, the pump plunger is lifted by the cam and camshaft driven by the engine. So, this cam and cam, so the pump plunger very important, pump plunger is lifted by the cam and camshaft, by the cam and cam follower, cam and cam follower driven by the engine. So, driven by the engine. So, this is very important. So, cam and cam follower that will be driven by the engine, and that movement of the cam follower will try to lift the plunger, and from where we are getting the pressure in the pump cylinder. Fine. Now, when the plunger is at the bottom of its stroke, both the intake and spill port are uncovered, and when the it is very important. I am not, again I am discussing here that when the plunger location is like this, that means both the spill port and inlet port are uncovered, right, very important. And when the plunger rises, these two ports are getting sealed. I mean, it will remain sealed for a while, because I do not know the length of the plunger. So, maybe the length of the plunger is not equal to the length between the port and the delivery valve seat, but so we are having a distance between valve seat and the inlet port. So, the length of the plunger may not be equal to that, but length of the plunger is such that whenever plunger is moving or lifting because of the movement of the cam and cam follower, so these two ports will remain sealed until unless the plunger distance is not covering that port location. So, initially these two ports are uncovered, but the movement of the plunger will try to seal both the port. But the compressed fuel leaves the delivery valve and begins injection period. That I said that compression of the compressed fuel leaves the delivery valve and fuel injection starts, and during the high velocity of the plunger stroke. But if the plunger continues to rise, that is what I was telling, that plunger will continues to rise, then spill ports is uncovered by the helical relief on the plunger. So, this is the helical relief, I can say this is helical relief, helical relief. So, plunger movement is continuous. So, whenever plunger continues to move or continues to rise, spill port is uncovered by the helical relief of the plunger. So, I am not writing again. So, initially both the ports are uncovered, the movement of the plunger will try to seal the port. So, rather I am writing. So, initially both the ports are uncovered, but the movement of the plunger and uncovered, but when the plunger rises, movement of the plunger sealed, movement of the plunger due to rotation of the cam and camshaft, makes both the ports to be makes the ports are to be sealed. This is very important, are to be sealed. Now, but when plunger continues to rise, the spill port is very important, spill port is uncovered, uncovered by the helical relief on the plunger, by the helical relief on the plunger. So, this is the helical spring, helical relief. So, this is control rack and helical relief, sorry this is not. So, I have shown that these are the helical relief this is a helical relief which makes the seal to be uncovered. Very important that whenever plunger continues to rise, the spill port is getting uncovered because by the helical relief. Now very important is that but at this point high pressure oil above the plunger escapes through. So it's very important. So whenever plunger is again lifting or continues to rise, the spill port is getting uncovered because by the helical relief on the cylinder, and then the high pressure fuel that might escape through the escape through the slot and through the spill port into the sump. So this is a slot. So this is the slot through which high pressure oil escapes from the top of the plunger and it goes to the sump. It is very important. While the delivery valve, now question is, this is very important. So initially we have seen that when plunger continues to rise, the high pressure developed that opens the delivery valve, and then fuel flows to the delivery line and it goes into the injection site, and then now I will discuss that how this needle getting lifted up. So now if we try to recall that, fine, it is very important that, see, this is the nozzle needle face. So so the perpendicular to this face will be the force. So if I try to decompose this component in two sides, one is this and another is horizontal and vertical. So this two horizontal component will try to balance each other, while the vertical components will try to lift the needle by an amount through which the fuel will discharge into the cylinder. This is very important. Now, so whenever high pressure fuel is striking the needle face or needle face surface of the needle, then there are two horizontal components balance each other. There are two horizontal components they balance each other, while the vertical components will try to lift the needle by an amount and it will open the orifice through which fuel will discharge into the cylinder. Now as I said you that if the plunger continues to rise, then this spill port is uncovered and certain amount the high pressure fuel on the top of the cylinder will try to leak from the helical relief, and that they will try to escape through this spill port and goes to the sump. But question is very important. So when the delivery valve, when the pressure reduces because of this leakage or some this through the spill port, then delivery valve will close. When delivery valve close, pressure in the delivery line reduces, but it is not completely. So there will be certain amount of pressure that might help in the next stroke, but that delivery line pressure is not good enough to maintain or to lift that needle so that the fuel discharge will stop. Now what will happen, very important part is that whenever the delivery valve is closed suddenly, maybe the pressure inside the delivery line will reduce, and that pressure won't be able to sustain the upward movement of the needle, as a result of which needle will, since it is spring loaded, needle will try to sit over the orifice. So fuel discharge into cylinder will stop, but there will be a pressure in the delivery line. Now again sudden stop of the needle into the orifice, again it will try to create a surge. I mean, whenever, it is very important, this is disadvantage. So when the delivery valve suddenly close because of the drop in pressure in the pump side, the injection side, the injection valve needle will be closed. As I said you that this is a spring loaded valve, pressure will fall again, and the fuel in the discharge tube and will be closed, and the fuel in the discharge tube feel a pressure. So when needle close suddenly, then fuel in the discharge tube will feel a shock, that is a pressure from the injection valve into the delivery valve will pass in the form of a pressure wave. So that as it close, which will be transmitted in the form of pressure wave through the discharge tube into the delivery valve. So what I am telling, when needle close suddenly and the fuel in the delivery line will feel a shock, and a pressure wave will transmitted from the needle side into the delivery side. Since delivery valve is already closed, that pressure again will try to come back from the delivery valve into the needle side, and that whenever that surge is again coming back from the delivery valve into the needle side, that again will try to uplift the needle by very small amount, and through which a certain amount of fuel will be discharged into the cylinder, and that is not recorded at that time. So whenever the system is designed to supply required amount of fuel, what we can see, the sudden closure of the needle because of the drop in pressure in the pump side will provide a surge in the form of a pressure wave, and that will transmitted from the needle side into the nozzle side, into the pump side. Since delivery valve is already closed, so that pressure again will be transmitted or coming back from the delivery valve into the needle, that is in the injector side, and when that surge is coming back from the delivery valve into the needle, that will try to create a small amount of lift of the needle, through which certain amount of liquid will be discharged into the injection cylinder, though it is not required at that time, and this entire phenomenon is known as after injection. So this after injection means, although the injection time or injection period is over, till there is a little bit amount of fuel that will be injected into the cylinder. This is undesirable because of this mechanical, because of this phenomenon, that is sudden closure of the needle will provide a pressure surge, and that surge will be transmitted from the needle side to the delivery valve side. Since delivery valve is already closed, that surge again will try to come back from delivery side into the needle side, and that surge will try to lift the needle by very small amount, and through which a certain amount of fuel will be injected into the cylinder, and this is known as after injection. So this is the important drawbacks of having this drawback of this particular system. So this problem can be avoided if I try to remove, or if I try to remove the delivery line from the system, and as if I put the pump on the top of the cylinder or on the top of the nozzle, in that way this problem can be eliminated. And if I try to put a pump exactly on the cylinder, or like the top of the cylinder or at the top of the nozzle, and that is what is known as unit injector, that I will discuss in the next class. So with this I stop here today, and we will continue our discussion in the next class. Thank you.